Per walks over here, I'll introduce him quickly. Our next speaker is Per Stenstrom. He's a professor at Chalmers University of Technology, also coming to us, honored by it, from across an ocean from Sweden. And Per has also done remarkable work in computer architecture and helping drive things along, as well as great contributions to the community, both in Europe and globally, with conferences and recently by trying to reboot one of our journals to make it perhaps useful. So, sorry about that part. And with that, I'll let him, talk now about what the future is.
Right.
So.
See if we can get things up here. If I just push this button, maybe. Doesn't seem to detect. Do this again. Something is happening here.
Okay, now it's the others.
Okay, good, great. Okay, so as previous speakers, I like to talk about what I'm very interested in the against the background of the major challenges we are confronted with in computer architecture. So I call it towards efficient computing. We have heard a lot of perspectives on that. But before that, let me see, where's the main person? Okay. So, Yale has certainly taught me a lot. I've known Yale for a couple of decades now, and he used to come over and enjoy Viking stuff, sailing and things like that. And as we are talking about Vikings, in fact, he taught me that Vikings, they were really well aware with Huffman coding. They knew that, they used a few words and they wanted to code them very efficiently. The Swedish name for island is okay? So there's something in the salt water that made me interested in computer architecture. So here are kind of the so threats and opportunities. I would say challenges. Challenges is a much nicer word. Of course, we are faced with a lot of interesting challenges ahead, and the ones I would like to pick up on in this talk is, of course, one that many people are worried about now, that parallelism is ubiquitous but hard to deal with. Of course, are we going to really make the major breakthrough to make use of parallel architectures to speed up any program out there? That I like to talk about a little bit. The other one is, of course, also that has been mentioned. Paris is heavily constraining performance growth. Obviously, we have to improve substantially in terms of efficiency in computing. And the last one is I like to spin on is that Moore's law is running out of steam. But that opens up a lot of interesting opportunities for us. And I think it's a fascinating era in computer architecture. I remember in the 90s, in the late part of the 90s, I'd become a new professor at Chalmers and said, am I really going to be excited until I retire in this field? Because it was just, so easy to incrementally improve things. But then, of course, there was this shift to parallel architectures, and now that we are facing that technology scaling is certainly not as effective as it was. It's really a fun playground to be in. Okay, so back to Yale again. So Yale used to come to Chalmers pretty regularly, I would say, and he always asked me. I like to teach in some classes for the freshman students, and it's so amazing. I really try to learn what is his secret recipe to get these youngsters so excited. You can see 200 undergraduate students, and they just start, to ask questions and things like that. So I used to jump in and try and also take advantage of this. And here is how Yale often starts things with the transformation hierarchy, right? And when I was listening to him, I said, hey, there is a problem with this, in fact, as we are moving forward. The problem is that we layer things, and that, of course, is an inherent source for inefficiency. So my first take on this transformation hierarchy is to drill a hole and put a tube. And the reason for that is that I like to solve one of the problems that Yale used to tell the undergraduate students, that, you know, electrons, they don't speak English, right? But I like to fix that by, you know, you just scream in this tube, electrons do my task more efficiently, and roger that, right? But there is a serious thing about this thing that I'm really interested in, and that is actually that I think it's really it's a very interesting research avenue to look at how we can get information transferred across the layers, and that is what I like to talk about. So I just embarked on a new project funded by the European Research Council. I call it MECA, Meeting the Challenges of Computer Architecture. It's not very innovative, but anyway. And in this project, we are going after what we call the 3 Ps. One is paralysis management. And actually, I agree with previous speakers that there is really not any inherent difficulty in writing a parallel program. What is really the challenge is what paralysis management, how we're going to move this parallel program to new platforms, and still it's going to enjoy the performance of that platform. So our take on that is actually to have the programmers do what they are good at, writing parallel programs, solving problems, making innovations at the functional side, but also provide information that is natural for the programmers down to the resource manager. Actually, I missed one. I think I missed one to comment about this. So I also added another layer here because that's what I like to talk about a lot, the resource management layer, okay? So the resource management layer is actually what Matteo said, you know, the runtime system, or you could think about it as the runtime system that gets information from the programming model or from the architecture to do a much substantially better job in managing the resources. So that's the first P I like to talk about. The second P I like to talk about is, of course, power consumption, okay? So even here, there is an opportunity also for the programmers to provide information to the resource manager, okay? And to do a much better job in managing the resources. And what I truly think there is a lot of opportunities is to express quality of service attributes. For example, I mean, there are obviously a lot of computational tasks that do not need to finish on a best effort. They can actually sit around and then be scheduled later or run a little bit slower, so there would be an opportunity there to save a lot of power. So that's one thing we are considering also. The last thing is I call predictability. One should remember that computers are used obviously a lot in embedded systems. I live in a city with where Volvo is one of the bigger employers. And of course, even they have started to use multi-cores, so parallel architectures are also under the hood, okay? Really under the hood. And so you have to deal with, obviously, also timing requirements. There's also a possibility, so then, obviously, you need to do as good a job as possible to meet the deadlines, but also there's an opportunity here that you don't have to run on a best effort basis. You can slow down when you see that you make progress and you're close to the deadline, and use that opportunity to save power. So in a nutshell, what we're looking at is actually what we can gain from having interaction between the layers. And that is from the programming model, of course, information that is easy for and natural for the programmer to expose, propagate that, try to bring that down to the resource management layer, and then also use that which is tightly integrated with a chip to control the resources at the microarchitecture level. And of course provide also monitoring capabilities to do that. Let me talk a little bit more in depth into these 3 Ps, okay? So as far as parallelism management, Matteo talked a lot about the opportunities around runtime aware architectures. One aspect that I've been particularly interested in is actually what we see in modern task-based data flow programming models coming out of BSC with OpenMP 4.0, and that is a way actually to express dependencies between tasks, okay? So this has been motivated by the fact to actually avoid barrier synchronizations. So you can have point-to-point synchronizations between the tasks. But it actually also gives a possibility, very useful information to, for the resource manager to manage the cache hierarchy. And that's where I come from, basically, where I've done a lot of work. So I got fairly interested in that avenue, I would say. More specifically, what you could do, examples of optimizations at the cache hierarchy level would be to use these dependency annotations to actually make cache coherent substrate as efficient as message passing primitives, right? So one of the problems with cache coherence is that it maintains coherence on the block level, on a, you could say, design time fixed entity. Whereas if you get this information from the programming model level, then you can actually support bulk data transfer. So shift, you know, a lot of data from one task to another in a more efficient way. You can also proactively, when the producer is done with modifying the data, you can ship it over to a task that is about to get scheduled, or doing the other way around of supporting prefetching. And you can do a lot of other optimizations at the cache coherence level, like supporting migratory sharing optimization, to get rid of a lot of the traffic overhead that is plaguing cache coherence solutions, okay? So we have started to look into those opportunities. I don't have time to go through it, but we see a lot of opportunities there to improve communication using this approach. Other interesting opportunities here as well that we like to investigate, and that is, how am I doing time-wise? 5 minutes, good. No, that's, sorry?
You have more than 5.
More than 5? Oh, I can speak slower. I can cool down. I can save power, so I can start. Good point. Actually, that's a good point, yeah. Really what I like to, the view I like to here is to see the runtime system having the same role as far as the cache hierarchy as the virtual memory manager or the virtualization layer or hypervisor has today for virtual memory, okay? So really, by getting this information, the runtime system or the resource management layer can do a much better job in managing on-chip cache resources. So that's something we want to explore deeper, and have started some work on. It's also a way, I mean, to use these annotations to speculative parallelism, and also an idea that has floated around that I've always found intriguing, and is actually moving the computation rather than moving data. And as Bill Daly pointed out, data communication is very expensive as far as power consumption. So really, I think there is something that can be done here. And again, using these annotations, I see a possibility to really come up with new innovations as far as using this moving to computation rather than moving data. All right. The other P, so now I probably just have 1 minute left, right? I'm soon done. So power management, what's my take there? Again, what if the users could express how long time a computation must take, and then what if the resource manager could track progress of a task against the deadline, and actually also having the knowledge of if I schedule this task to another core or give it more cache resources or whatever, how would that affect the time? I think this is a pretty interesting domain to explore, because then we could actually be more efficient in terms of controlled throttling of resources and scheduling of computations on heterogeneous substrates. So this is also something that we are want to explore in this newly started project. Finally, predictability management. So I actually did some work in the past on, well, in fact, it's a funny story. So when I came to Chalmers, they were really interested in embedded computing, and a colleague of mine said, oh, you have been working on caches. We used to turn those off in real-time systems. Well, I say, you cannot turn off a cache. You know, that's the most precious thing, and I've spent so much time on figuring out how we design efficient memory systems. So I really asked myself, this can't be true. And so we started a project to really come up with tight bounds on the worst-case execution time using caches and modern microarchitectures. And we did quite some interesting improvements there. So I've been really fascinating then of the problem of really taking a parallel application and really can we guarantee the sufficiently tight worst case execution time on a parallel application. If we can that, then that could actually again open up all these opportunities to start to run it slower, give it less cores, etc., etc. But this is a very hard problem, but not, well, it's a very challenging problem, and this is also something we are working on. It's pretty unexplored terrain to do that. And something that really opened my eye as an opportunity is actually a few years back, people at the University of Washington came up with what is called deterministic multiprocessing, because that's an important tool to really guarantee that communication events are deterministic in a parallel application. And we're using that as a starting point to explore how to come up with efficient use of offering predictable execution times. I think it's time to stop there with this nice picture again. Questions?